Welcome back to Statistics 568, Design and Analysis of Experiments. Today we're going to be starting Chapter 4 in my notes. It's pretty exciting. It's on factorial design. So let's get into that. Now, we're going to begin our study of factorial designs by looking at the full factorial design, specifically the 2 to the k design. That means all of our factors are going to just have 2 levels. Doesn't sound too exciting yet, but there's k of them, and that means we're going to have 2 to the k observations. So with 10 factors, we now have over 1,000 different observations to work with, and lots and lots and lots of interaction terms to consider. So this is going to be pretty exciting. Let's jump into it.
And we're back with another lecture of Statistics 568, Design and Analysis of Experiments. Today, we will be starting Chapter 4 of my lecture notes, which goes into the factorial design. So when we started this course, we did one-way ANOVA. Then we moved on to two-way ANOVA. This is effectively like k-way ANOVA. We're going to have lots of different experimental factors. At first, they're all going to be binary valued. So it's basically on or off, right? Apply or don't apply that specific factor to the subject. Now, the question is, how in the world are we going to test all of these different factors? Well, that's going to get us into the factorial design. So in some sense, it's nothing more profound than what we've already done. We just have a lot more factors to deal with. And again, we always have to be a little bit careful with the idea of economy and efficiency, because we don't want to be testing a giant group of subjects, probably because we don't have the energy or the money or the resources to actually do it. So that'll take us into many different extensions from the factorial design, like how to do blocking for factorial designs, how to do fractional factorial designs to reduce the number of the sample size required, and many other complications that will come in these lectures. But first, we're going to start with sort of the simplest setting, which is just the full factorial design. So let's go see what that's all about. Chapter 4 on full factorial designs. Specifically, what we will write these as are 2 to the k designs. So the rough idea here is we have basically k binary experimental factors to test. Now, because we're in this setting, right, we have lots of different combinations that we need to test. And we're going to need a fairly big sample size to do it. We also have to be a little bit careful now about the terminology, because in the previous lectures, I kind of used treatment and factor, experimental factor and treatment interchangeably, because typically we might have only had one experimental factor, which would then be the treatment applied. But in this case, if we have k factors, specific combinations of those factors would correspond to a treatment. So if I have, let's say, 6 factors, then the specific binary settings for each of those would correspond to one treatment, if that makes sense. Hopefully when we go through this, I'll try to be a little bit careful with the terminology so we can get this right. Now, so the first thing I want to do is just show you what you might have. So, and let's do an example. An example which is going to be a 2 to the 3 design. And we're typically going to assume there's no replications without replication. Now, you can, of course, replicate these things, especially if a 2 to the 3 would only require 8 observations, because 2 times 2 times 2. But when you have, say, a 2 to the 10, now you have 1,000 observations, or 1024 to be precise. So replicating that would take a lot more a lot more resources, right? A replication would effectively double the amount of resources required to run your experiment. So not to be taken lightly. Regardless, what we can do is, if for our example, our 2 to the 3 design, we can define A, B, and C to be our factors. And then we're going to have our response, or our data. And well, let's just write it in here. We're going to have y1, y2, y3, y4, y5, y6, y7, and y8. Why did I write all of this? I wrote it so that you can get a sense of what the design would look like. Now, each of these factors, A, B, and C, are going to have 2 settings, basically an on and off, or a plus or a minus. So for these binary factorial designs like this, these 2 to the k designs, typically we'll use -1 and +1 to denote the 2 different settings for each factor. Again, A, B, and C could just be additives to the soil that you're going to throw on your flower pots, for example. And you could either say add factor A or don't, add B or don't, add C or don't. Similar to whatever, some sort of medical trial. Maybe it's a cocktail of blood pressure medication, and you could say, take pill A, but don't take pill B, but do take pill C. So that's kind of the rough idea. Anyway, the way we often denote these are through pluses and minuses, just for convenience. So what we can do is we can consider all possible combinations of pluses and minuses. And you could also do binary 0 and 1 if you really wanted to. There's lots of ways you can represent these, right? They're just symbols, but for convenience, and also for a little bit later when we look into things like confounding and aliasing, this notion of plus or minus 1 will be nice, because there's actually going to be this interesting connection to the mathematics of group theory coming up in a moment. Well, maybe next lecture, but for the time being, we're just going to stick with, we're not going to worry about that. We're just going to have our basically our binary values for our factors. Right, so this would be the rough idea. We have a couple things that we have to recall, definitions, like we have the idea of a balanced design. So this is something we talked about before when we had like the incomplete balanced block design. Roughly, it just means that each factor level occurs in the same number of treatments. So what I said before was that basically each row is a treatment. It is a specific combination of experimental factors. So there are 8 different treatments in this study. If I were to replicate it, there would still be 8 different treatments. We would just replicate each one twice, if that makes sense. So for the balanced design, there we are, blue. Okay, yeah, so to have a balanced design, it means that each factor level, so each plus or minus occurs in the same number of treatments. So basically each factor level, e.g., let's say A plus and A minus, occur in the same number of treatments, rows. So what does that mean? That means if we come over here to each of these columns, we see equal pluses and minuses in each column. So you can count them if you really want. There's 4 pluses and 4 minuses in each column. This is what we want. We want to make sure we have a balanced design. And that's going to lead to the idea of having an orthogonal design. Orthogonal design, another nice property. So it says if two factors have all of their level combinations occurring an equal number of times, then they are said to be orthogonal. So basically, it's a pair of factors is, a pair of factors is, I guess, not are. A pair of factors is orthogonal if each combination of factor levels occurs an equal number of times. An equal number of times. So that's kind of like this idea of balanced, but now what we're doing is we're considering all possible, we're doing all the different combinations. So for example, if we were to look at B, let's switch the color and really mess this up, right? If we're looking at B and C, then we would say the combination of minus and minus occurs once, and it occurs twice down here. And similarly, if I can change this slightly to a slightly different red, the combination of minus n plus occurs once, and minus n plus occurs again. So the point is that every combination of factor levels, but with two factors, that is, occurs twice in this design. So minus minus occurs twice, minus plus occurs twice, plus minus and plus plus each occur twice. And specifically, they occur with differing values for A. So here we have minus minus with a minus, and here we have minus minus with a plus. So that's really where this idea of orthogonality is coming from. This, if you recall, the balanced incomplete block design is kind of like that lambda, the idea of factor pairs occurring in the same block. It's a similar idea. In this case, what we're saying is that the levels of B and C, well, a specific combination of the levels of B and C has to occur the same number of times as all other specific combinations of the levels of B and C. So hopefully visually that makes sense. Saying it out loud is a little bit confusing, but that's roughly the idea that we want. And I guess if all factor pairs are orthogonal with each other, then the design is said to be orthogonal. So the orthogonal design, I should say, is if all pairs are orthogonal, then the design is orthogonal. Orthogonal. So you could have the case where you have a balanced design that's not orthogonal if I forget to carefully align the pluses and the minuses. I can still have 4 minuses and 4 pluses in every column, but if I didn't do it in just the right way, we would no longer have that nice orthogonality property. And the orthogonality property is, well, very important. It's going to allow us to, in some sense, estimate everything, all the main and interaction effects. I guess it's independently the right word. I think it's the right word, of each other, because we're averaging over all other factor level combinations. Right, so okay, so we still have some of the same notions that we talked about in the previous chapter still occur here. We have the idea of restricted randomization. So we'll say, maybe not green. We'll say as with the split plot, we may have restricted randomizations restricted randomization in the sense randomization, can't spell and speak at the same time. So like with the split plot, we might have this restricted randomization setting where we have to, e.g., randomize A first before B and C. So that could be the case, or we could just fully randomize it, because if we were to try to run this experiment, my example here, my 2 to the 3 factorial design, we would take our 8 rows, and we don't want to test them in order. What we want to do is randomize the rows. So now we just have all of our rows in a random order, and then we would test them one by one, or maybe it's the setting where we could just test them all at once. Like if we have a group of subjects and we're feeding them a cocktail of drugs, then you just sort of hand everyone a little cup with pills in it, and you say, okay, everyone do it. But there are cases a lot of the time where we have to test these in some more sequential way, and we'd want to randomize this. Now, if we can fully randomize this, that would be great. We can't always do that. Sometimes we would have to test A at all the minuses first and then all the pluses, or vice versa. So that's the idea of restricted randomization. It's really just like what we did with the split plot. And the other thing is that we can replicate this. But we should always re-randomize for each replication. So much like all the other designs we talked about, you can replicate this. It may be it's going to double your sample size, so that may or may not be feasible. But regardless, if you do replicate that, you want to re-randomize everything again. You don't want to test you don't want to test your treatments, the rows, in the exact same order as you did last time. So it's always good to take that into account. All right, so, well, what are we going to do? Well, let's talk about main and interaction effects. And how in the world we're going to test these things, especially given the fact that we may not want to actually replicate our experiment. So the goal is we want to consider all effects, which would be the main and the interactions. And that would be, for example, A, B, and C, as well as AB, AC, and BC, and the three-way term A, B, C. So that's going to be, in general, this is 2 to the k minus 1 things to estimate. And that's a lot. So what we can do is we can sort of build this up one level at a time, starting with the main effects. So just to make sure it's clear, the main effects would be like A, B, and C. They're just the factor itself. The interaction effect will then be anything from 2-way to 3-way, 4-way, whatever interactions, going from the lowest order to the highest order. So what we can do is let's first talk about main effects. So what we're going to do is now consider a 2 to the k design with factors A1, A2, all the way up to AK. Now, we can define here the main effect. Well, we have a couple things. First of all, note that the sample size is capital N, which is 2 to the k. I'm assuming that I'm not replicating at the moment. Now what we can do is we can write down the main effect, ME for main effect of, let's say, factor I. So maybe I'll put that in blue here. Main effect for AI. Because I'm indexing the factors 1 through k, I'm not going to write a in there. I'm just going to say I for the ith factor that we're testing. Now, okay, so what would the main effect be? Well, in some sense, it's the difference between what happens when AI is at the plus level and when AI is at the minus level. So what do? Well, we average everything. We take y bar, we average all of the observations such that that factor I is at the plus level, and then we subtract the average where factor I or AI is at the minus level. So that's the notation we have here for I plus and I minus. And what do we have here? Well, these are averages over 2 to the k minus 1, with the minus 1 is now up in the exponent, observations. Basically half of the data set in each case. So we kind of split the whole data set in half. Remember, the design is balanced. Go back up here. That means we have an equal number of pluses and minuses for every factor. Hence, when I want to average all of the pluses together and all of the minuses together, and then I do a difference. And because of orthogonality, we have something that's quite neat here. So what I'll say is, due to orthogonality, every level of the remaining factors is considered. Maybe what I mean by considered is kind of a vague term, isn't it? What I mean is summed an equal number of times. What I mean by that is that if we fix AI to be at the plus level, and then we sum over all of those observations, for all of the other factors, we're going to be summing an equal number of pluses and minuses. So in a sense, if there are other factors that are still have some significant effect, they're going to cancel out when we estimate this main effect. So let's go back up to that table that I'm drawing all over just to look at. And the idea is that what if I were to sum up, let's say, if I took factor A here and fixed it at the level plus? Well, what that means is now I have B, which is minus in 2 cases, and B is plus in 2 cases. So in some sense, I consider the same number of minus B's and plus B's inside of that average Y bar, Y bar I plus, and similarly for Y bar I minus. So that's why this orthogonality again is important. It's kind of, at first you're like, okay, yeah, you just make sure every combination occurs an equal number of times, but it's really important when you're estimating the main interaction effects so that you in some sense average out all of the other factors, and all that's left is the factor I that you're interested in studying. I mean, in this case, we're going to do main effects for everything, but luckily we can calculate each of them. Right, and we can go a little bit further from that. So this was let's say the main effect with a big squiggly dot. Now what we can do is we can consider the conditional main effect. Conditional main effect. Now, the conditional main effect is kind of what you would expect when I say condition. We're going to be computing the main effect for I once again, but we're going to condition on, let's say, factor j having the value of plus. It could have the value of minus, it could have whatever you want. In this case, we're just going to set j to have the value, condition on j having the value of plus. So notationally, I can write this out as I plus and y, not y, j plus minus y bar I minus j plus. And what we're doing here is average over all y's with I at the plus level and j at the plus level. So now we're actually averaging over a quarter of our data set because we've cut it in half and then we cut it in half again. So now we have a 2 to the k minus 2 in the exponent, to be precise. So this is gonna lead us to the idea of an interaction effect. But effectively what we're doing here is we're just doing a conditional version of our main effect with the goal that we can eventually get to the idea of an interaction effect. So the interaction effect is what? Well, what we're going to do is we're going to start with the interaction effect for two factors, which is going to write it as int, for lack of a better notation, between I and j. So if we want to know how do factors I and j interact, they have two levels each. So there's kind of four different settings, plus minus for each of them. Now, the way we can define this is going to be 1/2 of the difference between the main effect of I given j at plus minus the main effect of I given j set to minus. Okay. Now you might be thinking, well, wait a minute, does this make sense? So yes, you can actually rewrite this symmetrically and note that this is also equal to ji, which is also equal to just flipping the order of j and I. If you write out the terms using the definition above, I don't really want to do that because it's just going to be a lot of terms to keep track of, but you can flip all of these around and they still kind of make sense. Now, that's a two-way interaction. How do we get to three-way or higher? So to get to a three-way or higher interaction, first what I'll point out is that this is two-way. And then what we'll do is we'll do conditional two-way interaction. Conditional two-way interaction. And there we're going to do this exactly the same way we did it before. We're going to use the notation, the interaction between I and j given a fixed value of factor L. I'm going to use L and not K because K is the total number of factors that I am testing. So we'll say if L is fixed at a plus, what's the interaction between I and j? Now, mathematically, it kind of looks, or notationally, it looks a little bit awkward and messy, but intuitively, all we're doing is we're going to the L column and we're only taking those observations where L is equal to a plus. So we've cut our data set in half. And now within that subset of our data, we want to look at the interaction between I and j. So it's the interaction of I and j for a fixed level of L. And we can write that really kind of by just including a second conditioning, which is going to look like the main effect of I given j at plus and L at plus minus the main effect of I given j at minus, but L still at plus. We're not changing the level of L. And then we can define the three-way interaction. Coming off of that, we're almost done, okay? And then we'll get on to some other stuff. Let's say, and then we have the three-way interaction. And the three-way interaction we can define, or mathematically, I just selected a whole bunch of stuff. There we go, we're good. The three-way interaction we can write down as between ij and L. And in this case, it's just going to be 1/2 times the difference between the conditional two-way interaction of I and j given L plus minus the two-way interaction, the conditional two-way interaction ij given L minus. All right, and we can just keep extending this further and further, building up all of our main effects. Okay, and I'll just say, and so on. For higher interactions. We can go to 4-way, 5-way, and so on, up to, I guess, k-way. There would be exactly one k-way interaction where all of the factors are interacting at once. But this is roughly what we're doing every time we compute one of these interactions. So note that much like, I changed the color scheme. That's quite interesting. I didn't realize I could do that. Note up here, it's like half green and half black. So that's a little peculiarity of OneNote. Anyway, what we have down here is that even for a three-way interaction, we're still averaging half, maybe not averaging, but each of these terms is sort of disjoint halves of the data. So if we were to unravel this mess, we would find out that the first conditional interaction and the second conditional interaction are dependent on the data sets, the data points, y, but 2/2 of the data set. So each of those is going to be a function of 2 to the k minus 1 up in the exponent data points. And yeah, we're going to be looking at the difference between them. So in some sense, when we're computing all of these main and interaction effects, we're finding every possible way of taking half the data, up to the orthogonality, every possible way of taking half of the y's and subtracting the other half of the y's, and then finding different ways to do that by fixing the values of certain factors. So ultimately, yeah, we're just computing a whole bunch of differences between the data points at different levels. So for example, the main effect, if we go back up here, the main effect for A would be the average of the first 4 observations, or the average of the last 4 minus the average of the first 4. If we were to do an interaction between A and B, it becomes a little bit more complicated, but what we end up doing is we actually end up, say, taking the values where A and B agree, so the plus pluses and the minus minuses, averaging those together, and then subtracting the cases where A and B disagree, minus plus and plus minus. So that's where the interaction comes in. It actually says we want to compare when A and B are the same and when A and B differ in their factor levels. Now, that can be made more precise if we decide to write this down as a regression equation using, well, the XOR operator. So if you're into computer science or logic, you might like this. Otherwise, sorry, I guess. So we can define the XOR operator, which I'm sure every subject has their own notation for it. I'm going to use the plus with us inside a circle. And we get, I guess what they call, is this a truth table? I think they call it, whatever it is in logic. If we have two binary variables, A and B, and then we have their XOR. And XOR is the exclusive OR. So if I have, let's say, 0, 0, 1, 0, 0, 1, and 1, 1, then what I'm saying is do the two things agree or disagree? If they agree, I put a 1 in the last column. If they disagree, I put a 0 in the final column. Now, what we can do is we can map this multiplicatively to minus ones and plus ones and use multiplication. So if I map 0 to minus 1 and 1 is just plus 1, then we get the same type of result, which is if we get a minus 1 times a minus 1 is a plus 1 times a plus 1 is a plus 1. And if the signs are different, minus 1 times plus 1, I get minus 1s. So notice that these are kind of the same thing equivalently. It's just that I replace 0 with minus 1, and I replace the XOR operator with just, over here, we just use multiplication. We'll just use red. So this is one way to, well, this is just a logical operator that we're going to need, because if we want to write this factorial design as some horrid regression equation, we can do that. Probably don't want to do that, but we can do that. So let's just do it anyway. And in this case, if I have, let's say, given k binary regressors, x1 through xk, these are going to be my binary variables, or Boolean. They're 0 and 1, whatever you want to call them. And we're going to have something that's going to look like y is equal to an intercept term, beta naught, always an intercept term. And then we're going to sum from I, little I, from 1 to 2 to the k. And we're going to do beta I, the ith parameter. And then what we're going to do is we're going to do a big XOR. You can think of it like a big summation or a big product symbol or a big union. This is an XOR over all the, let me write xj. So over all the xj for j inside some subset script j sub I. And this is where that script j sub I is going to be the set, an index set of j equaling 1 to k, such that the floor of I times 2 to the minus j mod 2 is equal 1. So, okay, basically what we're doing is we're just considering all possible ways of splitting up the index set in half. That's the fancy kind of math way to write it, but effectively all I'm saying, if we go right back up to that example from the top, is that there's different ways I can do this. I can take the first half to be minuses, the second half to be positives, pluses, as I do in the A column, or I can alternate 2 and 2 like I do in the B column, or I can alternate 1 and 1 like I do in the C column. So C goes minus plus minus plus minus plus, B is minus minus plus plus minus, and so on. A is just all the minuses first, all the pluses last. That's the roughly what this crazy expression is saying, in case this is a little bit disturbing to look at, but it's quite neat. Effectively, the point is I can write this out as a nasty large regression equation, and we could actually just go compute all the beta hats as usual, but we don't actually want to do that. So we could, emphasis on could, compute beta hat as some sort of X transpose X inverse X transpose Y, but typically this is, very big, very large to invert. I guess computers are pretty good these days. So when this was developed, 100, maybe not 100, but, 50 to 100 years ago, when people were talking about this stuff, when Fisher was doing it, I guess in the 30s or 40s, I'd have to double check that. But whenever he was doing it, right, you might not want to invert a 1,000 by 1,000 matrix. Now, okay, your computer can do it. Luckily, fun little side fact. Fun fact. You can estimate these betas quickly, beta hats quickly, thanks to a guy who worked with Fisher named Frank Yates. So smart guy, worked with Fisher. I believe he worked with Fisher. I should double check my facts, especially because this is all being recorded forever. But Yates, sorry, with an S. Frank Yates, who has a clever algorithmic way to actually compute all of these beta hats so that you don't have to do a giant matrix inverse, because that makes everyone unhappy when you actually have to do that. Nobody really wants to go through all that headache. So, actually, no, is that the problem? I don't think that's the problem, because all of the columns of the design matrix should be orthogonal. So I don't think you actually have to invert that. I think it's more just, I think it's this piece, right? Very large to multiply. Typically in a designed experiment, because of all the nice orthogonality conditions, this thing is diagonal. It doesn't destroy my original point, which is that you don't actually want to have to do a giant vector matrix multiplication here, when you could have a clever algorithmic way to kind of fight your way through it. But yeah, but just to be precisely clear, in this case, I believe the design matrix should be orthogonal, or not orthonormal, because it wouldn't normalize to 1. It would probably normalize to like n or something, because you're summing up the same thing, or k, because you're summing up the same thing k times. But regardless, I'm going to stop rambling. Yeah, there's better ways to estimate this than doing least squares, than using the LM function like you would and doing least squares. Anyway, yeah, so there's a couple other things to note. One is that we have 2 to the k fx, I guess 2 to the k minus 1. Well, if we have the intercept term, but we'll just ignore that. We have 2 to the k minus 1 fx to estimate. So, and each requires 1 degree of freedom, because there's 2 factor levels. It's a binary factor, 2 factor levels minus 1 number of degrees of freedom, and we have, 1. So we have 1 degree of freedom for every main and every interaction effect. Hence, without replication, no DOFs, degrees of freedoms, for the residuals. That doesn't going to stop us, though. So we're not done yet. Just because we have no degrees of freedom for our residuals, we can still estimate all of the main and interaction effects. We just don't have any degrees of freedom left in that case to actually compute the residuals. So we're going to find some workarounds that don't require replication. But if we were to do replication, well, I'll say if we were to replicate n times, then the residuals would have how many degrees of freedom? Well, they would have the total sum of squares, which would be 2 to the k n times 2 to the k minus 1. This is the total sample size. I'm not done yet. This isn't the answer. This is just the first part. Total sample size. And then you'd have to subtract all of the degrees of freedom used to estimate main and interaction effects. So we would subtract a 2 to the k minus 1, which is the number of DOFs used for estimation. And we are left with, well, the minus 1 and the plus 1 cancel out, and we're left with an n minus 1, 2 to the k. So we'll actually have a ton of degrees of freedom for the residuals. It's one of the reasons why people don't like actually replicating these experiments, because every degree of freedom is something that you can test, something that you can estimate, a hypothesis test that can be performed. And if you have an extra, even if you replicate twice, that means you're going to have an extra 2 to the k degrees of freedom just sitting there for the residuals, unutilized in some sense. So ideally, you wouldn't. You can get some more statistical power to detect things, but it comes at a big cost, because you'd much rather use those degrees of freedom to test more hypotheses. So that's kind of like the goal we're at here, is this maniacal kind of approach to hypothesis testing, where it's like we want to grab every degree of freedom we can and use it to test something. And that's what we're going to try to do. So if we don't replicate, well, there's a couple things we can do, and I will save the R code for the next lecture. But so just keep some of these ideas in mind as we write them out on paper, and I'll show you how they work in R in the next lecture. Because we're gonna get to Lenth's method. Good stuff. All right, one approach, one alternative approach. I'll say instead of replicating is to just compute the main effects and I'll say interaction effects. Because I don't really want to write all that out, and used a QQ plot to look for large effects. So this is very ad hoc, it's visual, it's not exactly the most precise compared to, say, a hypothesis test, but you could just plot them and basically look at all, because you have the ability to estimate all of the main and all of the interaction effects, and that's exactly what the AOV function in R would do. Now, if you don't replicate, you're not going to get any F statistics, you're not going to get any p-values, but you still have main and interaction effects. They're all in some sense on the same scale, because they're all using two halves of the data set to estimate. So you can just stare at them and say, well, where's the large ones, right? Both in the, well, I guess in this case, it would be sums of squares. So they should always be, I think they should always be positive. I should double check that. But regardless, you can just stare at them and basically say, okay, here are the biggest ones in magnitude. Are they significantly bigger than the rest? I guess the main and interaction effects as written down are not the same as the sum of squares, which is what I was confusing in my head. So you can look at the sum of squares in the ANOVA table, or you can use the linear model. You can look at the main and interaction effects. And the main and interaction effects would be put into a QQ plot. And you can basically just say, okay, do any of them look peculiarly large? That's a hard word to say. Are they kind of large or very negative or very positive in magnitude? In which case you might say, yeah, that might actually be something significant. Then you can do a follow-up study just to target those significant effects, right? We don't want to replicate another 2 to the 10 samples with most of these factors not being important. But if we can identify some that look like they might be important, we can do a follow-up experiment to test those more precisely. But I like p-values, and I'm sure you like p-values too. We can actually get a p-value out. It's not as nice as the F statistic, but it's kind of neat and a little quirky. And that leads us into the next part of today's lecture, which is going to be Lenth's, not lengths, but Lenth's method. Much like making sure that you don't autocorrect Tukey to Turkey, make sure you don't autocorrect length to length, because it could easily happen and it's just going to make your report look kind of silly. So Lenth's method is a way to get a p-value when the residuals have 0 degrees of freedom. So that's kind of neat that that's actually possible. Let's take a look and see how that's done. All right. So what's the problem? Well, the problem is that without replication, we have 0 degrees of freedom for the residuals. But what does that mean in practice? It means that we have 0 degrees of freedom to estimate sigma squared, the variance, because that's actually what we're doing in the denominator of the F statistic, right? We're trying to get a sense of the background noise so we know if the effect, the sum of squares, the treatment, or a specific factor sum of squares, if it's big or not. We can just stare at the number, but if we don't know what the scale we're on, we don't know if I give you a sum of squares of 25. Now, what does that mean? It means absolutely nothing unless we know what the denominator is. If the variance is very small, like 1, then 25 looks pretty big, again, up to degrees of freedom, which can also affect things. If the variance is 1,000, then 25 looks like nothing, again, up to degrees of freedom for testing every bit. But that's kind of the point, is that we can't estimate sigma squared. So the solution is find a new way to estimate sigma squared, or in this case, the square root of it, which would be the kind of the standard deviation, or in that case, the standard error is what we're trying to come up with, a new standard error. So Lenth in, I think, 1989, not 18, 1989, getting old, proposed a what's called pseudo EUDO standard error. So we know about the standard error, right, in statistics because, right, we would normally have, just to note, right, we would have our usual t-test. So recall t-statistics, which are going to look something like whatever, an estimate, we'll call it theta hat, divided by the standard error for theta hat. I mean, that's roughly what the t-statistic's doing. We're trying to estimate something, then we divide by an estimate of the standard, the standard error being an estimate, I guess, for the square root of the variance or the standard deviation. Again, we can't estimate the variance without degrees of freedom. So we instead compute a pseudo standard error, which I think is kind of a neat and quirky little thing. So what in the world is a pseudo standard error? Well, the PSE, or pseudo standard error, as Lenth defined it, is going to be 1.5 times the median of the estimated, I didn't define these guys. Let me define. So first we're going to say let theta hat I for I in 1 to 2 to the k be the estimated main and interaction effects. So rather than indexing them by some like super index, I, J, K, L, whatever, not K, because K is the total number of effects, or the total number of factors that we're testing, we're just going to say theta hat I is going to be the main effects and the interaction effects from 2 to 3 to 4 to k-way interactions. So there's a lot of them, right? And like I said up here, about to run off the screen, that's what we would plug into a QQ plot just to stare at them and say, okay, are any of them large or not? What Lenth's method does is says, let's use these estimated main and interaction effects to get a pseudo standard error. So what you do is first you get something that looks like that we want to compute the median of these, but we're not computing the median of the absolute value of all of the theta hat I. We're only computing those that fall such that, I guess there's supposed to be a hat there in my written notes, is less than 2.5 times the median of all. So we have nested medians, right? Isn't this wonderful? Something that looks like that. So what in the world is a nested median thing doing here? Well, let's draw a picture because I think that will help explain it. If I have my line here, this is 0, and this is, I guess, off to, this is just the real line. Now, I have a whole bunch of theta hats that I is supposed to be inside the absolute values, not outside. There we go. So what I would have is a whole bunch of thetas that would be somewhere. Maybe there's some ones that are far away. These are the theta hat I's. So what, let's see, 1, 2, 3, 4, 5, 6, 7. Okay, I almost, is it 2 to the k or 2 to the k minus 1? I think it should be 2 to the k minus 1. Yeah, excellent. So it should, yeah, of course. Sorry, this is supposed to be minus 1. Just to be precise, it doesn't make a huge difference, but we're not including the intercept term, the null term in here. We're just considering all the different, we're considering all of the different main and interaction effects without the intercept. So getting back to this, if I have my 2 to the 3 design here with my 7 dots, it looks like 3, 3, 4, yep, good, 7 dots. Then the first thing I do is I start on the inside and I find the median. So the median is just the middle point. The median is here. Then what I do is in absolute value, I guess in this case, everything's happening on the positive real line because I should actually be doing this in absolute value. Okay, so what we're going to do, just to make this, I lost my entire line there. We're going to move the origin because strictly speaking, everything should be done here in absolute value. For this to make sense. So we find our median And we say, okay, there's the median of the absolute value. And let me put an absolute value here to indicate that we're looking at the magnitude of the theta hats, not their just absolute or their specific position on the real line. And then what we do is we expand this by 2.5. So I'm going to not do this to scale. And then we're going to say maybe over here is 2.5 times the median. And then what we do is we take all of the thetas that lie to the left of that line. Basically, we throw out this guy over here. So we get rid of that guy because he is, in some sense, an outlier. He lies more than 2.5 medians from the origin, right? It's kind of like if you were to take 2.5 standard, if you just had data and you computed the standard deviation and you said anything that lies outside of 2.5 standard deviations from the origin is an outlier, and I'm just going to get rid of it. The reason he does this is to add a little bit of a robustness. So he first says, compute the median just of all the data, then throw out anything that's too big, because the thought process is that this may be significant, and we only want to use non-significant theta hats to compute the pseudo standard error. So the intuition here is that, right, what we want to do is if we have a bunch of theta hats that are in some sense null in the idea that there is no significant effect there, then we want to take all of the theta hats where there's no significant effect and use those to estimate the pseudo standard error. It's kind of like saying, well, these theta hat are not interesting. They're just random noise. We can use that random noise to estimate the pseudo standard error. Anything that is not random noise, anything that has a strong signal in it, we want to throw out. So that's what that inner expression here is doing. It says throw out any outliers, then take the median again, but this time running out of colors up here. Maybe we can use that other slightly different red. There we go. So then what this guy says is actually take the median of the remaining points, in this case, the new median lies maybe halfway in between those, because I threw out 1 point. I have 6 points, so it would be, let's say, halfway in between points 3 and 4. Then expand by 1.5, and you have something called the pseudo standard error. 1.5 is actually just a really convenient approximation. I'd have to double check to see exactly where that came from. I'm pretty sure it had something to do with canceling out the coefficients in the half normal distribution, but I'm going to have to double check that. I think it's like the square root of pi over 2 or something like that, but don't quote me on that, because I would need to double check exactly to figure out where that 1.5 comes from. But roughly that's the idea. So the idea is throw out outliers and compute the new median. Okay, so we've done that, and then the claim that we're not going to try to prove, because it's kind of annoying, but I guess you can read up on Lenth if you really want, is that in a 2 to the k design with specifically IID normal 0 sigma squared errors, as is always kind of the case that we want in this course, then if theta 1, notice there are no hats here. These are the true main and interaction effects that we're trying to estimate. If all of them are 0, so in this case, nothing at all is interesting in our data experiment, then, maybe I should say if this, then the pseudo standard error converges in probability to sigma, the square root of the variance or the standard deviation as n goes to infinity. This would be like if you kept replicating it and you just had lots and lots of data. I think it should be n goes to infinity. I'm just wondering if it was actually supposed, it shouldn't be k, but maybe it should have been k actually goes to infinity. I'm going to have to double check that. Regardless, as the sample size goes to infinity, whether we're taking whatever that means. So again, the idea is that Lenth's method is assuming that we want to take the thetas where theta is or the theta hats where the true theta is equal to 0. There's nothing interesting going on there. And then given that we believe this claim, we get I'll call it T-like statistic. I do like T. And the T-like statistic is going to be the T, I'm going to write PSE I for the pseudo-standard error, and then what it's going to be is just theta hat I divided by our pseudo-standard error, with no index because it just is what it is based on our data. So then the question is this significant or not? Well, we're not going to use a T distribution. We're going to use, something a little more complicated. And the idea is that we can compare these T PSE I's to a significance threshold. So just like we would do with a t-test or a chi-squared test or whatever, we'd pick a threshold and say, if my test statistic exceeds that threshold, it is deemed significant. Reject the null. There is some significant main or interaction effect here. If the estimated effect is not greater than that threshold, then we fail to reject the null. We don't reject the null. There are two different thresholds. We'll say there are two thresholds given some alpha. Given some alpha greater than 0, the test size. The first has I guess, a couple different, where is it? Yeah, a couple different names. We have the IER, which is the individual error rate. Error rate. And the individual, there it is. The individual error rate is kind of like the uncorrected threshold, the threshold that is not corrected for multiple testing. It's sometimes called the marginal error rate. And in this case, it's just going to be a number such that the probability that the pseudo-standard or the T-like statistic in magnitude is greater than this threshold, IER sub alpha, to indicate that we're doing this at test size alpha, given that we're in the null hypothesis setting, which is whatever I corresponds to, whatever interaction or main effect that I corresponds to is not significant, then the probability of a false positive is alpha. This is for each I. So in contrast, we can also compute an EER, which is an experiment-wise error rate, or sometimes it's called, I'll say, or simultaneous error rate. And this is kind of exactly what you think it would be. It's looking at the maximum. It's looking at all of the statistics, t statistics at once. And it's picking a threshold for rejection such that the probability, we'll say I from 1 to 2 to the k minus 1 of t PSE I is greater than, there's a little typo there. Actually, this is supposed to be EER. Alpha is conditioned on, I guess, the null hypothesis for all of them, I guess, has to be equal to alpha, or yeah. So the idea here is this is really just saying the individual error rate is the, run the test. It's not corrected for multiple testing. The experiment-wise or simultaneous error rate says correct this for multiple testing. Pick a larger threshold, because we want to make sure that we don't get too many false positives. Now, in this case, you very often don't have to worry about getting false positives because you're using kind of a conservative method to start with. We don't have that nice F statistic. This is a little bit more finicky, and oftentimes you may not be able to detect significance using this, which leads to some interesting advice. So we'll end this lecture with some advice. Advice 1, which comes from the textbook by Wu and Hamada, the one that I used when I was first trying to figure out what to teach in this course. And the claim is that it is preferable to use the uncorrected threshold, as 1, the corrected threshold is too conservative, and 2, it is better to include an uninteresting effect, false positive, than miss a significant one, false negative. So says those textbook authors. So their claim is use the IER so you don't get a false negative. Now, of course, in practice, you have to consider the cost of a false positive versus a false negative. One may be worse than the other. Neither is good, but one may be worse than the other. Now, we also have advice 2, which came directly from reading Lenth's work. And what Lenth said was basically this method should not be used in replicated experiments where the standard error can be estimated more efficiently by traditional analysis of variance methods. So basically, Lenth says, don't do Lenth's method if you replicate, i.e., have degrees of freedom for the residuals. Again, it's a pretty neat tool to be able to compute a pseudo-standard error when you don't have any degrees of freedom left to compute a standard error. But it's not, my understanding, and I have not tested this myself in simulations, but my understanding is that it doesn't have the same power as the f-test if you were to just use the f-test. Now, I haven't tested that in practice. It actually would be quite a neat thing to do because you could simulate factorial experiments in R and then determine how frequently do we actually correctly reject the null hypothesis given using an F statistic versus using Lenth's method. I just thought it was an interesting quote coming from Lenth that he says basically, don't use my method if you have degrees of freedom to just do the standard analysis of variance. So thank you, Lenth, for, I guess being humble about that and not just saying, use my method all the time. It's awesome, as so many people often do. Okay, so I think that'll be the end of today's lecture. One more thing I did want to mention, though, before we end is that I forgot to mention this. I will mention this in the next lecture, but just to keep it together, you can find Lenth's method in the BSMD. Pretty sure that's it, right? B lowercase s, M, capital D package in R under a function called length plot, which will give you a nifty plot where you can look at the magnitude of all the effects in that you're testing in your factorial design. All right, and we're going to look at that, but we're going to save that one for the next lecture. So see you there, and we're going to have a lot of fun trying to actually apply some of these methods to actual factorial data experiments. So let's do that, but next time. See you then.